Hi, everyone. Welcome to the December Sky Talk. Thanks for coming out, everyone. I'm just going to introduce today. We have Julianne Goddard, one of our postdocs, giving the presentation tonight. So you can
That's kind of a famous space name, isn't it?
It is, yeah. No, I wish I could claim relation, but no. Yeah, so I'm Julianne. I love that you gave me the credit of being a postdoc, but I'm not. I'm just a grad student. I haven't graduated yet, so I'm still just a grad student. Pre-doc, yeah. And tonight I'm going to talk to you about things beyond the stars. So this title is a little bit vague, but basically the gist of what I'm going to talk about tonight is extragalactic astronomy. So things that happen outside of, let me see, why aren't you moving forward? There we go. Things that happen outside of the Milky Way. And I'm going to take sort of a past, present, future approach to talking about it. So the main thing I want to start with is just, how did we get from, early human views of the firmament and the heavens to realizing that there are other galaxies, and not only other galaxies, but billions, maybe trillions of other galaxies. And then I want to move on to present and talk about how we study these objects that are outside of the Milky Way, that are at the distant edges of the universe. And what sort of things we can learn by using different tools that are available to us. And then finally, I'll conclude with just a few comments on some of the major unanswered questions in these fields. So starting out, I have on this slide our early universe, but really what I mean to say is our early human perspectives on the universe. So as far back as we have recorded history, what were humans thinking about what our universe looked like? So originally we didn't even really know, there was something separate from the Earth. It was just the Earth, everything we can see, that's all there is. About the 5th century BC, we have a record of philosophers or the astronomers of those days observing a lunar eclipse and saying that the shadow that moves over the moon has a curve to it. And from that, they deduced that the Earth is actually a sphere and the spherical shadow is moving over the moon. And so that was the first time we sort of have the spherical Earth that's separate from the heavens. A couple hundred years later, we have the first measurement of the size of the Earth. So that's sort of the first measurement of the size of our universe, of what exists. And that was actually a surprisingly accurate measurement. I'm not sure how to say it, Eratosthenes. Eratosthenes, that sounds much better. So he used shadows of objects at different locations on Earth at the same time to estimate the curvature of the Earth and therefore the size of the Earth. And he estimated the Earth's radius to be about 7,000 kilometers. And today we know that it's about 6,300 kilometers. So really a very good estimate given the technology they had at the time. So that's sort of the image we see here. That was the picture that we got from those sorts of theories and measurements that we have the Earth, and then surrounding the Earth, we have sort of these different rings of the heavens. The very outermost ring held the stars because these seemed fixed and unmoving. And then they also saw wandering lights, which we now know are the planets. But at the time, they didn't know that. They just knew they seemed to move relative to the stars. They called them wanderers. And people began to try to predict the motion of these wandering bodies. And it was Ptolemy in about 140 AD that came up with a model that did a pretty good job of predicting where these wandering lights would be in the night sky at any given time. And his model was still an Earth-centered model, but he thought that these objects, these bodies, orbited the Earth, but that they also moved on smaller orbits inside of those orbits, because you had to explain the fact that these planets, though they seem mostly to move in the same direction in the sky, sometimes they stop and move backwards and then progress forward once again. So he explained that using epicycles, or orbits within orbits. And because this did a pretty good job of predicting where the planets would be, this remained sort of the view of the universe for almost 1,000 years. Other astronomers sort of refined it to make it more accurate, and also spent a lot of time cataloging stars and other objects in the night sky over this 1,000 years, but there wasn't really a big change in the view of what the universe looked like. I do want to mention in this picture I put here, this is from one of the stellar catalogs. This is the constellation Andromeda. And it was noted that this object on the belt sort of looked fuzzy, like a cloud. It didn't look like a regular star. And of course, they didn't know what that meant at the time, but we will discover later what that actually was. So moving forward, 1543, Copernicus publishes his work on a sun-centered model of what they then thought to be the entire universe. So he made a model similar to Ptolemy's, however, he moved the sun to the center. So now the planets are orbiting the sun rather than orbiting the Earth. And this really made waves, of course, because humans don't like to be the center of the universe. We still don't like to be the center of the universe. So it wasn't accepted immediately. It would still be several generations before this was accepted. But his model wasn't perfect, but it did do a better job than Ptolemy's at predicting the planetary motions. It wasn't quite as complicated. It didn't involve so many cycles within cycles within cycles in order to explain the planetary motions. Moving forward, we also have the new technology of telescopes coming into play. So the telescopes allowed us to resolve objects in the sky that we had never seen before. And Galileo is famously one of the first scientists to have a telescope and to really publish a rich record of what he observed using that telescope. So in this picture down here, this is actually one of the pictures that Galileo wrote in his sketchbook when he observed one of these fuzzy objects, like the one in the record that I showed previously of the Andromeda constellation. So he looked at these fuzzy objects and realized that they were actually composed of lots of tiny individual stars. And this really just blew out the size of the universe that was expected at that time, because that meant that these objects have to be so far away that not only are they composed of many stars, but these stars are so tiny, we can't even see them. So that means the universe is so much bigger than we thought it was. And additionally, he observed things like the moons of Jupiter obviously orbiting Jupiter and not the Earth. So this was sort of definitive proof that not everything just revolves around the Earth. There are things that obviously revolve around other bodies. And so this was really the definitive proof that the Earth is not the center of the universe, but it still took some time. Even Galileo was heavily persecuted for publishing this information.
I remember that telescope. It looks all fancy and metal, but it's really worse than the worst telescope you could get at Walmart nowadays.
It is, I know, yeah. You actually don't get much improvement with those old telescopes. It's amazing that the things they were able to discover with such a low level of technology. I think it said I read somewhere his first telescope only magnified like three times the size. Okay, so now moving forward, the Earth is no longer the center of the universe. And I kind of want to shift the focus of this whole conversation to these fuzzy objects, because that's really what we're interested in when we talk about discovering other galaxies, because we know what these fuzzy objects end up being. So it was in the mid 1700s that Immanuel Kant, the philosopher, published work talking about the idea of what if these objects that we now know are composed of so many stars are like island universes, like the world we see around us, but so distant that it's like a whole second universe. And he is credited with coming up with this phrase island universes, which was used for a long time to describe these other galaxies. At the same time, we were finding more and more of these because we were getting better and better telescopes. So Messier, he was credited with compiling the very first catalog of nebulae. And nebulae at this time really refers to anything in the sky that looks fuzzy. So we now know that this applied to galaxies, it applied to supernova remnants, it applied to stellar clusters, and it applied to what we now call nebula, which are, stellar nurseries, actual clouds of gas and dust, which is what they thought all of these were originally before the advent of the telescope. So we are starting to find more and more of these. Of course, not all of them are actually galaxies. We'll find out later when the technology gets better what each of them actually are. But the first catalog had 45. It later grew to over 100 or over 100. And of those, 39 we now know are galaxies, and we still use the same titles given to them by that catalog. And then we have the Herschel family developed an even more extensive catalog of these nebulae, over 5,000. And all this time, we still don't know what they are. We don't know that, there's this growing suspicion that they're island universes, but it's not globally accepted, if you will. In the mid 1800s, we had the development of spectroscopy. First, it was stellar spectroscopy, but eventually led to spectroscopy of these nebulae as well. And this really opened up everything for the field of astronomy. So if you're not familiar, spectroscopy is the study of light. So if you shine light through a prism, it diffracts and it breaks up into all of the wavelengths that are composed in that light. So if you shine white light through a prism, you get a rainbow. If we take light from a distant astronomical object and diffract that light, we end up seeing individual colors of light. And that's called emission spectra. And those individual colors of light tell you the chemical composition of the object that you're looking at. You can get more information than that out of it as well. Due to the Doppler effect, we can see if these wavelengths of light, if these colors are shifted, we can tell how fast the object is moving relative to us. And what we now know about the expansion of the universe, that also tells us its location. At the time, they didn't know that. At the time, they had the development of the Bohr model. They were understanding better interactions between light and matter. So they did know about the chemical composition, and they knew also that we got information about velocity. So in 1912, Vesto Slipher used spectroscopy to look at some of these nebulae and found that some of them were moving at enormous speeds that we don't see inside the Milky Way, greater than the escape velocity of the Milky Way. And so this was another big hint that these objects are not inside our Milky Way. We have the famous Great Debate of 1920, which a lot of people credit with being the turning point between a universe, which is only the Milky Way, and a universe composed of many, many galaxies. It's also said that maybe this debate wasn't really quite the turning point that we give it credit for, but it did sort of focus in on these big ideas of not only are these nebulae island universes, but also it focused on the size of the Milky Way. How big is the Milky Way actually? And it also was the turning point for us knowing where we are in the Milky Way. At the time, it was actually mostly widely accepted that these island universes were outside the Milky Way, except this astronomer Harlow Shapley very much disagreed with that notion. He thought, no, it's just that the Milky Way is much larger than we thought that it was. And he also had done studies on globular clusters to show that the sun was not, in fact, at the center of the Milky Way, which people had previously always just assumed that it was. So we have Harlow Shapley arguing these objects are actually inside the Milky Way. It's just the Milky Way is much larger than we thought it was. And then on the other end, we have Curtis, who's done a lot of observations of the Andromeda galaxy, M31. And he has evidence not only from the spectra, but also from the presence of multiple nova occurring in that region, that this is in fact not inside the Milky Way. He argued that supernova events are pretty rare in our galaxy. We don't see very many, but he observed several occurring just in this one little fuzzy patch in the Andromeda galaxy. And so he said, this can't possibly be inside our galaxy. The number of nova happening here are too many. And at the end of this debate, there wasn't really a decisive conclusion. I think most people already agreed with Curtis that these objects aren't in the Milky Way, but really, we got a decisive answer just a few years later from Edwin Hubble. He looked at M31 and found a Cepheid variable star. And these are stars that vary in brightness over a fixed period of time. And that period over which they vary in brightness is directly related to how bright they are, to their intrinsic brightness. So because of that, even if you see one very far away, if you can measure its brightness and how it changes over time, you can then determine what its true luminosity is, compare that to its apparent brightness, and figure out how far away that object is. So he used these Cepheid variable stars to measure the distance to M31, to this Andromeda galaxy that we now know, and found that it could not possibly be inside the Milky Way. It was much larger than even Shapley's estimate for the size of the Milky Way. At the time, I think it was like 900,000 or about 1 million light years away, which we now know it's actually about 2.5 million light years away. So it's even further than he thought it was. But even with his lower estimate, it still was definitive proof. This cannot be inside our Milky Way. So we now knew there was at least one of these, and he continued this work. He found many more Cepheid variable stars in other galaxies, and so proved that there were many of these other island universes, and also ended up finding the expansion of the universe using this method, because he found that the farther away galaxies were, the faster they were moving away from us. And so was able to show that the universe is expanding as well. And he, this was a whole new world. Suddenly the universe was so much bigger than we ever thought it was before. And this is sort of the end of the first part of what I wanted to talk about. That's how we got here, how we got to knowing we're not the only galaxy. Universe is way bigger than we thought it was. And I'm going to sort of skip over the next 100 years because there's a huge amount that happens here. And really what I want to talk about is extragalactic astronomy itself. So here is just very, very briefly some of the big things that happen to lead to our modern cosmological model of the universe. We had, like I already said, the discovery that the universe is expanding. Hubble found that experimentally, but at the same time, Einstein was publishing his theories of relativity And other scientists were finding solutions to those equations that showed that the universe should theoretically be expanding. So it was sort of at the same time being found theoretically as it was being found experimentally. In the mid-1900s, we had the discovery of the cosmic microwave background, which was strong evidence for the Big Bang model of the universe, and also gave us a whole rich new field of studying the early universe. In the 70s, in 1970, Rubin and Ford, this was not the first evidence for dark matter, but it's probably the most cited one. They discovered that when we look at how stars are rotating in galaxies, there's evidence that there's a lot more matter present in that galaxy than we can actually see in stars and gas. So that was sort of the most definitive proof for the existence of dark matter. And we also found, it's not listed here, but we found that the expansion of the universe seems to be accelerating with time, which is evidence for dark energy. So all of these things lead us to sort of this inflationary Big Bang model, which includes lambda called dark matter. So we have a universe that's roughly 75% dark energy, 25% dark, well, what was it, like 23% dark matter, and some small fraction of the universe is what we actually see. And also during this 100 years, we have huge advancements in technology, not only in telescopes on the ground, but also space-based telescopes. And we also have the development of computers, which have hugely contributed to our capabilities. So I have a video here, which shows a collection of galaxies which have been observed using the Sloan Digital Sky Survey. So this shows about 400,000 galaxies. These are actual images taken and showing where they lie relative to each other in the universe. And what I think is fascinating about this is that, like I said, this is only like 400,000 galaxies. So not only is this only a small fraction of the galaxies in the observable universe, it's only a small fraction of the galaxies observed in this one galaxy survey. And we have tons of these surveys in all different wavelengths, and optical, infrared, UV, all the way across the spectrum. And so we just have now this enormous amount of data. The problem now in extragalactic astronomy is not lack of data. It's more often, how do we process all of this data and fit it together in a way where we can actually learn usable, definitive information from it. So I'm going to go over some of the most, outstanding methods that we use to look at galaxies and other objects outside of the Milky Way. I already briefly talked about spectroscopy. It was developed back in the 1800s, but it is truly invaluable. I mean, this tells us, we aim the telescope at a galaxy, we can know what elements are present there. Sometimes if there are extreme magnetic fields, we can tell that those magnetic fields are there. We can tell how far away this galaxy is. We can get information about the velocity dispersion of the stars there. And by looking at galaxies in different wavelengths, we can understand the actual structure and makeup of the galaxy. We can see, is there cold gas there capable of forming stars? Is there active star formation that typically shines in optical and ultraviolet wavelengths? Is there a lot of dust that shows up in infrared telescopes? We can see the presence of hot gas either in a galaxy or more often in galaxy clusters, which are galaxies that are gravitationally bound to one another in a cluster, and they are surrounded by extremely hot gas that shines in X-rays. So we can figure out what sort of material is in the galaxy and where that material is by looking at these galaxies in all the different wavelengths of the electromagnetic spectrum. This is just an interesting sort of side note. I mentioned how we have all of this data from all of these different galaxy surveys that span all different wavelengths and different stretches of the sky, different redshifts. And one way that we've actually come up with to help process all of this data is using citizen science, where we actually crowdsource anybody who's interested to look at these images and actually classify them. Because we know galaxies can be classified. This is the Hubble tuning fork diagram that shows the different galaxy types. We have ellipticals and spirals, some that are barred, some that are not, and we have lenticular galaxies. So anyone who wants, I think Galaxy Zoo is one of the most famous of these projects, but there are many others, can sign up for this and then get access to all of these images and actually assign classifications to these galaxies. And when this is done over and over by lots and lots of people, we actually get really good, reliable classifications. And people use these in scientific journals. If they need a collection of, barred spiral galaxies, they'll go to Galaxy Zoo and pull the ones that have been identified as barred spiral galaxies. So this is actually a great way. And there's a lot of other things like trying to find galaxies with rings or things like that. I think Galaxy Zoo is actually not running anymore, but I checked recently and there are lots more. There was one, this ringed thing where you're trying to identify galaxies with polar rings. They said there's actually an app you download and you just sort of swipe left or swipe right for if it has a ring or no ring. I don't know. I just think this is really interesting and a really great way to get classifications for anyone who's willing to
And people
participate.
discovered some weird things there too that they had to go back and further study.
Yeah, definitely. Yeah, just a great way to process all of that information. Another way that we do this, which I didn't make a slide for it, and I really should have, is with machine learning, because machine learning can also do the same thing, right? You can train a machine learning algorithm to identify a particular type of galaxy, and then it'll go through all of this data and pick out the ones that fit what you're looking for.
Yes, ChatGPT.
Well, in the way that we train those algorithms, which is what I'm going to talk about next, is numerical simulations. So if you want to train a machine learning algorithm to look for, I don't know, a barred spiral galaxy, you can simulate hundreds of thousands of barred spiral galaxies and then feed those, this is what you're looking for. So you feed those images to the machine learning algorithm to train it and then give it the real data, and it's able to identify very well what you're looking for. But numerical simulations in and of themselves, apart from that application, are enormously helpful for really understanding how these large scale structures evolve. So back in the 1980s, these were really starting to be developed to the point where you could use them to do astronomy, these numerical simulations, computer simulations. And they were actually part of the development of the lambda cold dark matter model of the universe, because we were in simulations using this model, using Newtonian gravity, using, I guess those original models didn't include these other things, so I shouldn't say it. But they were able to show that if you use cold dark matter instead of warm dark matter, you get a lot better reconstruction of our physical universe that we actually observe. So they were able to show that cold dark matter is a better option for what dark matter might be than warm dark matter. And that's sort of what we do with these numerical simulations. So, you know, you use all of the modern physics that you know about star formation, about, you know, how gas interacts hydrodynamically, dark matter, dark energy, all of that is put in, and then you just let it evolve over billions of years, over the age of the universe. And you're able to see the actual evolution of large scale structure forming. This image down here is the dark matter showing the formation of the sheets and voids. You're able to see the galaxy form. This is gas colored by density. In this little box, we have stars, so you get to see the formation of the stellar disk of the galaxy, and then this is just a zoom in of what we have here. This is showing the formation of a galaxy over about 10 billion years. So using this, we can study, you know, how something on a very small scale affects the large scale, not only the whole galaxy, but the CGM, the filament, the whole surrounding environment. And we can also see over time, you know, you can't ever see with observations, you just see a snapshot in time. So if you see a big bubble there, you think, oh, well, maybe this bubble was caused by a supernova, but you can't really prove that. You can only infer it. And with these, we can see, you know, a supernova actually blow a hot bubble in the gas around the galaxy, and we can study that. So even though it isn't the real physical universe, it does a really good job of imitating it and allowing us to do things that we couldn't otherwise do. Admittedly, I don't know very much about gravitational wave detection, but this is a relatively new field that is also teaching us about things outside of the Milky Way. It allows us to study black holes and neutron stars, their formations and interactions. And I think that with time, we'll find that we learn more and more from gravitational wave detectors. I see all the time that people are coming up with new ideas of, oh, maybe we could study this using gravitational waves. I think I saw recently that somebody proposed finding planets in other galaxies using gravitational wave detection, which I'm not quite sure how that would be possible, but that sure would be interesting. Okay, so this is the last thing I'm going to talk about, just a few of the outstanding issues in extragalactic astronomy. Some of these are sort of more on the cosmology side, but the lines between these are kind of blurred between cosmology and extragalactic astronomy. So one of the big ones is conflicting measurements of the Hubble constant, which is how quickly the universe is expanding. We measure this several different ways, but two of the big ones are either using models of the cosmic microwave background or using standard candles like the Cepheid variable stars, which is how Hubble originally measured it. But using these two methods, we find different values for this expansion rate, and the error bars don't overlap. Like, there's a small uncertainty here. These numbers are just decisively different numbers, and we don't know why. Maybe one of these two methods is inherently flawed, and we just don't know how it's flawed. Maybe there's just something about the universe that we don't know yet. There's something different than what our model suggests. So that's a big question. Dark matter and dark energy are still huge open questions. We're pretty sure they're there. We see all the evidence that they're there. You know, dark matter and dark energy does a really good job of simulating universes that look a lot like our universe. We don't really have another explanation for these gravitational rotation curves or the accelerating expansion of the universe. However, we don't have any idea what either of them are. We have a lot of theories for what dark matter is, but so far our detectors that have been designed based on those theories have found nothing. And so these are just big questions. Do we need to redesign? Do we need to find some other explanation, or do we keep hunting for these ones? And then moving more onto the actual like galaxy side of this, away from cosmology. Some of the big questions are, so I didn't actually talk about supermassive black holes at all yet, so maybe I'll just skip over that one. But well, most galaxies seem to host supermassive black holes, but they seem to be too big, too fast, based on our observations. In fact, a lot of galaxies seem to be too big, too fast as well. But one of the open questions is, where do these supermassive black holes come from, and how do they grow so quickly? So do they directly collapse from overdensities of gas in the early universe? Were there very massive population 3 stars in the early universe that collapsed into these black holes, or perhaps just lots of mergers? We don't know. So that's a big question. And then, of course, what is the evolutionary path of galaxies? So since Hubble, we've known that there are all of these different types of galaxies. We've got ellipticals, we got spirals, but we don't actually know how they relate to each other. Does one come first and then the other, or is it just completely dependent on environment? Is there an evolutionary path? And so far, there isn't a clear and obvious one. We see divisions like here. This shows if we plot galaxies by their color and their brightness, we can see that there's clear divisions. A bluer galaxy means that there's a lot of active star formation. A redder galaxy means that there's an older population of stars, and then green is somewhere in between. So we can see that these bluer galaxies tend to be fainter, they tend to be smaller, and they tend to be spirals. And the red galaxies tend to be ellipticals, and there are a lot more massive ellipticals. There are some faint ones too, or I guess, yeah, faint or small. So we don't know why this happens. You know, is there some sort of evolutionary path like the one shown here, which shows like a direct collapse of black holes from overdensities in gas, and mergers, growing galaxies, leads to rapid star formation, a lot of supernova activity, which destabilizes the gas, spirals inward to trigger feedback from the supermassive black hole as it's accreting all that gas that's coming to the center. And then that feedback goes to slow down the star formation, and then you end up with a red galaxy. So that's, you know, the theory of how we go from blue to red. But we don't have any definitive proof that this is what happens. So that's a really big question. But that's all that I wanted to talk about today. So thank you for coming. Are there any questions? Yeah.
I just have one quick comment. One thing that's neat about astronomy is how something unplanned, an unplanned discovery can just completely change paradigms that you don't see coming at all.
Oh yeah.
And the best example of that is one that you mentioned, which is, and I remember it was only maybe 15 or 20 years ago. It wasn't that long ago when there were only 3 possibilities on the future of the universe. Number 1, the acceleration would go, but gravity would slow it down and it would stop, and then it would reverse and you'd have a big crunch.
Mm-hmm.
Scenario number 2 is that the expansion would slow down due to gravity and it would just eventually just stop, but it would never collapse back on itself. Scenario number 3 was that the expansion of the universe would continue. It would slow down due to gravity, but not nearly enough. And the expansion would just continue on forever, although slowing down due to gravity.
Mm-hmm.
Those were the only 3 options. But then they discovered that the acceleration was increasing.
Mm-hmm.
The acceleration was accelerating.
Mm-hmm.
And that wasn't even one of the choices. That's how out of the box that discovery was. And that led to, you know, the concepts of dark energy and things like that. And that was not even on the radar until they made that discovery. They had to had some splaining to do, Lucy. So that's why I think astronomy is cool, is because just one discovery like that can completely flip everything on its side.
No, that's what I love about astronomy too, how just looking at the sky can completely change everything that we know about everything. It's mind blowing. It's
Mhm.
wonderful. Yes.
Do you want to go back real quick
Sure.
to the last slide?
Mhm.
What happened in like on the emerging problem in physics chart, like 2013? The CMB, the constant seems to like shift tremendously.
Are you talking about right here?
Yeah.
Yeah, I think these are just two different CMB models. So this is the
Okay.
WA map, and then this is, I'm not
Just-
sure what this is. This is probably, what's it called? The newer one. I forget what it's called. But yeah, that's
Okay.
what that is. Mhm. Yeah, so there's even conflicts within, these same methods, but they're a lot closer. Yes.
When you're looking at
Thanks, that's what it's called.
the first two types. But I've searched, what's the difference between the two types of sample?
I'm sorry, where,
The standard handles.
the two types of Cepheid variable stars? Yeah, so I don't actually know what the difference is between those two types, but I know that the fact that there are two different types is the reason why Hubble originally got these distances wrong, is because he didn't know there were two different types, and so he was using the wrong one.
Has its own.
Yeah. Mhm.
It might be something, not familiar with Stephen specifically, but variable stars in general. It might suggest a difference. Their brightness varies in different patterns, or they have, like size differences. There's some kind of notable, something along those lines, possibly.
Arguably would be the most famous star of the 20th century right there.
Right, yeah.
And amateurs can easily image it today, as I have, do different brightnesses with just a little 8-inch telescope that I can hold in my hand from my backyard patio.
Isn't that crazy?
Could do the same thing as the 100-inch hooker reflector back in, the 1920s.
Mhm.
Best named telescope ever. By the way.
Well, I think if nobody else has any, questions, we'll go ahead and conclude the Sky Talk there. Thanks again for coming out, everyone, and, hope you have a